wanted to, make an introduction, the first thing, and I'll be covering a little bit of what are the questions that are driving us in particle physics, or what are the things that we're studying. I'll also then tell you a little bit about this standard model, or the theory that we have so far achieved to describe all these type of phenomena, very, very small and very, very high energies. And then I'll go into a little bit of detail of what the Large Hadron Collider is, how it works, and then how we actually record those collisions with this compact muon solenoid detector, the CMS detector. And then I'll try to explain a little bit what we're going to do later in the afternoon with these computers to analyze these W and Z particles decays as they decay, and these events that we've recorded in the detector. And then I'll say a little bit about the tool that we're going to use, which is this event display that is called iSpy. And then in the end, the goals for today is to actually perform a few measurements. So your job will be to basically distinguish whether the event that you have in your screen is a W production or a Z particle production. Then you're going to tag whether the W is a positive one or a negative one. This is the electric charge. Okay? And then we can measure the ratio, so how many W pluses we produce as opposed to W minuses. You will also see how these W's decays and the Z bosons decay, and whether they produce an electron or a muon, and we can also measure that, and that also tells us something very interesting about nature. And finally, once you've tagged all these C candidates, we can measure their mass, and in the end, basically make a measurement of what that mass is, which is also a very useful parameter in all these theories. Okay, so that's basically going to be the goal for today. Okay, so let me just get started. So for particle physics, what we're trying to understand is the basically what's the nature of matter. Okay, and there are many questions that, even though we're in the 21st century, we still don't know about this very basic question. For example, the ultimate goal is to actually understand what matter is made of. So if you start from something in our everyday life, like a water droplet, for example, how that molecule is bound together, then what that molecule is made of, what the atoms are, and then if you keep going inside the nucleus, what those protons are made of, which are made of quarks, and then the final question is, do we actually have anything smaller than a quark? So are the quarks themselves composite? So that's one of the big questions. How small can we go in this reductionist quest, basically? The other question is, of course, how do these constituents interact among themselves? Are there any new particles that we still haven't discovered, even at this same level? As I said, can we actually break down these smaller particles into more fundamental particles? One of the biggest questions that you'll hear about also in the press lately is what is the origin of mass? So as I'll tell you, this theory that we have, in principle, writes down all the equations for all these particles and doesn't give them any mass. Okay? So we are still trying to find a mechanism by which these particles acquire a mass as they travel in the vacuum. Okay? And we still don't know that, which is, you would think, a very, very basic thing. So we still don't know that, for example. We also have to address one of the biggest questions out there, which is, why are we made of matter and not antimatter? Okay? And I'll come back to this in a minute. And we also, one of the biggest questions is, what is this dark matter? So if you actually look at the rotation, for example, of the sun around the center of the galaxy, and you count how much mass there is in between us and the center by how much light these stars are shining inside, it turns out that the mass that you measure in there is not enough to account for the speed of rotation of the sun around the center. So there has to be more mass that we're not seeing. And that's what it's called, this dark matter. And we think actually that they may be in the form of particles. Just a big halo of particles whizzing around the center of the galaxy. Okay? But still, we haven't discovered this, so we don't know what those are. And that's why it's called dark matter. Okay? And also the final question is, why is gravity so weak? As we'll see in a minute also, we have 4 forces in nature, and gravity, the one that we're most used to in our everyday lives, is the weakest of them all. And we still don't have a good description of how to fit that in with the rest of the forces. Okay. All right, so then let me just jump in straight up to this particle theory that we have. which is really a triumph of 20th century physics. And the picture that it gives us, it's a very, very simple one, that you can basically describe all the matter around us with these 12 particles, basically. So we have something called quarks, and there are 6 of them, and they're ordered by families. So the most basic ones are the up quark and the down quark, and then these two have, if you want, heavier brothers and sisters, which are the charm and the strange, which basically they share the same characteristics. So they have the same electric charge, for example. They have the same spin, which is a, if you want, a property of the particles, and they basically behave the same way. It's just that the charm is heavier than the up, and the strange is heavier than the down. And finally, you have a third generation of, again, the same type of particles, but now very, very heavy as well. So even heavier than this second generation of particles. And then down here, we have what we call the leptons, which are very light in mass. And these are the electron, which is the most familiar to us. And then the same way that this had heavier brothers and sisters, the electron also has a heavier brother, which is the muon. And that in turn has also a heavier one, which is the tau. Okay? So it really is a very, very beautiful picture that you can describe every atom that you see out there, every matter that we've ever discovered with this very simple picture. It's actually even more scary. You just need 3 particles to describe everything. And those are the ones in this first family. So the up and the down, and then the electron, that basically gives everything. So we are all made of up, down, and electrons. That's it. You don't need anything else. Okay? So the picture that this theory tells us is that we then have all these 12 particles that give us matter, and there are also 4 other particles that are actually the ones responsible for making the forces. Okay? And these are what they're called bosons. So we have the photon, which is the particle that carries light. So it's the most abundant particle in the universe. And this one is exchanged now, billions and billions of times between your eyes and what we're seeing around us. But it's also the one responsible for electricity and magnetism. So whenever you're plugging in something in the outlet, in the wall, photons are being exchanged all the time. Okay. Then we have the W and the Z bosons. Those are basically responsible for nuclear reactions. And this will be the topic of our day. And then you finally have gluons, which are the ones that are basically binding together all these quarks to form protons and neutrons and other composite particles. Okay. And that's it. So this really is a very, very, very simple picture. And the idea is that you have 2 types of particles, matter particles and force particles. Okay. So again, let me come back to this very simple picture that you just need up and down quarks to form a proton. Actually, a proton is made of 2 up quarks and 1 down quark. And then a neutron is made of 2 down quarks and 1 up quark. Okay? And when you put this together and then add an electron, that's it. You have atoms. And then when you begin adding more protons and more neutrons, you have the whole of chemistry, right? So that's your periodic table of the elements. It's just combinations, protons, neutrons, and electrons. Okay? And that basically gives us and the Earth, and all the galaxies, and all the light that we're seeing from outer space. So you really, again, this is why I said that you really only need these 3 particles. Okay? Then these other heavier families, where we've discovered them is in high energy interactions. So they were, for example, present at the beginning of the universe. And when a very heavy particle from the sun, for example, hits the upper atmosphere with enough energy, then it produces these other like charm and strange and boson parts, for example, or muons. Okay? So we see those particles in our everyday life. It's just that they're not stable, basically. Okay? These heavier particles. So let me then come back to these 4 forces. So again, the ones that we're most familiar with is gravity and electromagnetism. But then there are 2 others, which is the weak nuclear force and then the strong nuclear force. And the key idea that perhaps you should get away from this talk is that these forces are mediated or are transmitted by particles also. Okay? So particles are not just making up matter, they're also the ones responsible for exchanging and the forces. Okay? So I've put here in this table these 4 forces ordered by strength, with the nuclear one, which is the strongest, just being factor 1. Okay? So gravity, as I was saying before, is super weak. That's why you need huge masses like the sun and the earth, or the earth and us, to be actually measurable. Okay? So it is very, very weak. The strength of the pull between me and another person is very, very small. Okay? So you really need a huge amount of mass for it to be meaningful. It acts on mass, so any object that has a mass will feel gravity. And then the range is very long, it's almost infinite. It just decreases as 1 over r squared. Okay, so the distance squared, that's how it decreases. The next one in strength is the weak nuclear force, which is 100,000 times smaller than the strong force. So now it's a little bit more in the same ballpark, but you see that there's a huge difference between gravity and this weak nuclear force. Okay? This weak nuclear force is basically talking between these electrons and these quarks. Okay? This is what we call fermions. And the particle that carries that is this W and the Z. And the range is extremely small. This is even smaller than the nucleus. This is smaller than all these quarks, actually. It's just very basically at the particle level. Okay? It's very, very tiny range. And again, this is responsible for all these nuclear and some of the radioactivity decays of atoms. And then finally we have electromagnetism, which is basically acting on charge. So whatever has anything that has an electric charge, or an electric charge that is moving, then will feel this force. And the carrier, as I was saying before, is the photon. And it has the same range as gravity, so it decreases as 1 over the distance squared. And the strength is 100th of the strong, so it's fairly strong. And finally, we have this strong nuclear force, which acts on quarks and the gluons themselves, and it's mediated or carried by gluons, okay? Which is basically, they are responsible for keeping the protons together in a nucleus, and then the quarks inside a proton also stable. And the range is within the nucleus. So the nucleus normally has a radius of 10 to the minus 14 meters. So 10 to the minus 15 meters is basically inside. It's a tenth of that radius. Okay. So one of the most brilliant discoveries of this theory was to say this, that it is the exchange of particles that is responsible for all the forces. Okay. So let me then just give you a visual picture of this. Imagine that you have 2 basketball players on an ice rink. So there's no friction between the soles of their shoes and the ice. And then they're exchanging, for example, or someone, the player number 1, throws the ball at the other player. What you would expect if they, because there's no friction with the ground, when the second player receives the ball, she will probably just go sliding backwards, right? So if she was static like this, ready to receive the ball, when she receives it, then she will just basically move backwards, okay? It's a case, for example, of conservation of momentum, okay? So if she had an initial velocity of 0, when she receives this, she cushions that, but then she will basically go backward. What we say is that she has changed her momentum, okay? So the mass is the same, but she has changed her velocity, okay? So there's a delta V, basically. There is a change in her velocity, okay? And we can equate this change in velocity in an instance of time with a force. So this is the same as if someone from the outside comes in and pushes her, okay, in the same direction as the ball did, okay? So the idea is that by exchanging this basketball, you have the effective same effect as someone poking it, for example, and producing a force, like a contact force, okay? So that's basically the idea of all these particles being carriers of forces, okay? So the matter particles are constantly exchanging these force particles, okay? And for example, that's why when you knock on something, that's actually what's happening, that I'm exchanging photons, basically, between the skin, the molecules in my skin, with the molecules on this table, okay? It's not gravity that is preventing me from pushing down this table, it is electricity, okay? So again, this is something that, we're doing basically without thinking, but this is the actual thing going on in there, okay? Okay, so then, I didn't say this, but in this table, we basically have to double all these 12 particles because there is something called they're anti-particle. So it's basically, for example, if the electron has a charge of -1 in whatever units, there will be a new particle that has the same mass, the same spin, the same interactions with everyone else as an electron, but it will have a positive, a +1 electric charge. Okay? And all of these particles, by the way, I should say, all of them have been discovered. The latest one was this top quark, which was discovered in Fermilab in Chicago in 1995. And their antiparticles have also been discovered. Okay, so we really are on safe grounds here. Okay, so this antimatter is really very weird. It has the same mass, the same spin, the same interactions, but then just the opposite electric charge. Okay, and the way it works is that if you have a positron, that's what we call the positive electron. Okay. And that positron sees an electron, they basically annihilate together and then give off light, or photons. And this is also something that we can use if we're able to generate matter and antimatter of the same kind and then put them together, then they will produce new energy with Einstein's famous formula, and then we can actually then use that new mass that then decays into some other particles, for example. Okay, so this is actually something that we use again. As a matter of fact, every day basically in our labs, okay, dealing with this antimatter. Of course, we cannot produce a lot of this antimatter because whenever it touches anything else, then it evaporates basically, right? So it has to be contained with magnetic field, and it has to be a huge vacuum and everything. But we are constantly producing these things. Okay. Now the observation is that we're not made of antimatter, and if you look out there, you don't see planets or stars or galaxies made of antimatter. So the question is, where did all the antimatter go? Okay. It is a valid assumption to think that at the beginning of the universe there was equal amounts of matter and antimatter. So what happened to that antimatter? Right? And that's a very good question, and we still don't quite know the answer to that. Okay. So the idea would be that if there was a big chunk of the universe with gas or even galaxies or even stars in the form of antimatter, in the interface with the matter chunk, then we would see huge annihilation and huge radiation, basically, or huge light bursts. Okay, but we don't see that. Observationally, we've looked back into the past and everything, and there's nothing. Okay, so we have, we basically now know that there was a mechanism by which, at the very early universe, all the antimatter basically disappeared. Okay, so we had tons of matter and antimatter, and these little white things are supposed to be like light, so photons. And then as time evolved in this second picture, then some of them began to annihilate with each other, until at the very end, you only are left with 1 in 10 billion matter for the original. So if you had 10 billion matter and antimatter particles, at the end of this 1 second in the universe, you only are left with 1 matter for every 10 billion antimatter. Okay? So this very tiny asymmetry, we still don't know how it happens. Okay? And this is also one of the things that we're trying to study. Okay? Why are we actually mostly made of matter? Okay, well, absolutely made of matter. Okay, so let me go back to the standard model. And this is now a different picture of those 3 families, but ordered basically by the mass. Okay? So these neutrinos, which are also like lighter sisters, if you want, of the electrons, are very, very, very tiny in mass. And then here you have, again, this first family, of which all of us are made of. And then you have here the second family, so the muon, which is the sister of the electron, and then the charm and the strange quarks. And then here is finally the third family. And I told you that the top quark was the one last discovered, and that's because it's the heaviest single elementary particle. Okay? This one single particle, as small as an electron, weighs as much as a gold atom. Okay, so like something like 200 protons put together. Okay, so it's a tiny, tiny object, but with very, very high mass. Okay. Okay, so this structure of why these particles have this mass is, again, one of the biggest problems that we have. We still don't know why this is the way it is. Okay. And here you finally have the W and the Z boson, and then this Higgs particle, which is what we think actually would give mass to all the other particles. Now, we know that the standard model, again, has been a complete, very, very success describing all the matter that we see around us, but we've now gotten so good at making these precision measurements that we know that it's not the complete picture, and it doesn't address all the questions that we have. So we know there has to be another theory up there that basically improves on the standard model. Okay. So for example, it doesn't address why there are only 3 generations. You could think that nature could have 4 generations. Why not? Okay. Or it doesn't even tell us why 3 and not 2. Okay. In reality, we don't need this second and the third. We are only, we're good to go just with 1. Okay. Although now we know that we actually need 3 if we want to explain this asymmetry in the universe between matter and antimatter, for example. So there are hints there that there's something else going on. We, for example, still have not discovered this Higgs particle, so that's also something that you will hear in the news this year, that we're actually very, very close to, we think, discovering this particle. Why that hierarchy of masses? That's also a big question, as I was saying before. There's also many free parameters that you can trick in this theory, and that's not a very nice theory, so normally you want something that's a little bit more simpler. And also, as I was saying before, gravity is not in the picture, so that's a big, big problem. Okay? And this is basically what Einstein kind of died doing. He wanted to basically unify all these other forces with gravity. Okay. So how do we actually measure these things? So for these particle physics experiments, these are basically like your biggest microscopes that we have come up with. Okay. So if you want to detect things that come from galaxies, for example, and the outer space, you can just use radio waves. Okay. That perhaps have a length of 100 meters or so. Okay. Now, if you want to begin seeing smaller things like dust, or for example, or something much smaller, then that's enough with visible light, for example. Okay, that's our eyes. And then, if you want to go below the level of a cell, then you will need something like a microscope, which is just basically a lens magnifying whatever you're trying to see. The problem is that visible light, at some point, you're using still visible light as your probe, okay, to see what's in your target there. Visible light at some point is large or larger than what you're trying to measure, okay? And visible light has a very tiny length of 10 to the minus 7 meters, basically. The oscillations in light is 10 to the minus 7 or so. So if you want to measure something and it measures 10 to the minus 8 or 10 to the minus 9, you cannot use light to actually poke at it and see what comes back, okay? Because this light will basically just go through and not seeing this very small object, okay? And so for that, you then need an electron microscope, which is basically, instead of using light, you use an electron that you have very high energy, and then this wavelength of that electron, so the oscillations, or how much it measures this electron, is actually compressed to something very, very tiny, as much as your 10 to the minus 10 object, for example. Okay? And that's what we do when we want to see something like an atomic structure in some sample, for example. So then you need this electron microscope. And finally, then pushing that to the limit, if you want to go then below the atomic scale, you then need electrons or quarks or protons accelerated at a very high energy, so that you basically are squeezing them into very, very, very tiny dimensions. Okay? And that's basically what we're doing. So we accelerate particles to extremely high energies and then smash them together to see what comes out. Okay? So for that, you need these detectors that basically will see what comes out. These are gigantic instruments that record these particles as they come out of the collision. Okay? And for that, you also need these computing grids to analyze all these huge amounts of data and then tell you what happened in that interaction. Okay? And finally, you also need a lot of people and universities to actually tender to these detectors and analyze all that data. Okay? So that's basically where this Large Hadron Collider comes in. This is a huge tunnel, 16 miles long, in between Switzerland and France in Europe. And the idea here, again, is like colliding two strawberries and then getting a whole salad fruit out of that collision, basically. Okay, that's really what we're doing in the end. So what we're trying to do is take one proton and another proton, accelerate them so that they have a huge energy, and then convert all that energy into new mass or new particles. Okay? For example, this W boson out of this. Okay? And we can do that with these very, very hard collisions. And the only thing we're using is this equation from Einstein, in which we're transforming the energy from the protons into mass, to the mass of this W, for example, into new particles. Okay? So this is a picture of the accelerator. This is basically the drawing of that. This actually is dug up and it's 100 meters underground. Okay? This is Geneva, in Switzerland, that's the airport of Geneva, to give you a little bit of the scale, and that's the Mont Blanc in the Alps. And so we basically have this huge tunnel with these two beam pipes, or pipes, that are evacuated in very, very high vacuum, and that's where we circulate all these protons, and then we make those protons collide in 4 experiments. Okay? And actually, we, here at Rochester, we helped build this one here, CMS. Okay? And CMS and Atlas, they're basically doing the same thing, and then these other two are doing other types of things that we're not going to cover today. Okay? So this is huge in scale. Okay? So let me give you a bit of an idea of what this is. You know, you basically need only 10 to the minus 9 grams of hydrogen to run it every day. We accelerate all these protons to basically that horrible number, which is very, very close to the speed of light. Okay? So, but remember, this is a massive particle. And so this is basically the analog of taking me, if I weigh 100 kilos, and then accelerating me until I become as heavy as basically a small truck, right? So this is, 350 tons or so, okay? So, well, actually, that's a very large truck. Okay, so, I mean, and this is, well, this is a little bit going into special relativity with how things move or how they behave when they go to very high speeds. And the reason why you cannot accelerate anything past the speed of light is because, you know, the closer you are to the speed of light, the bigger apparent mass they have, and then the more energy you would need to keep increasing their velocity. And so that's why we say that, you know, this is as taking someone from 100 kilos and then putting him at 350 tons. Okay? So that if you want to push it for that heavy truck to go faster, you would need a huge energy. Okay? Anyway, so they're going very, very, very fast, and that's exactly what we want. So we go from something that is very light, but we give it a lot of energy, so that energy can be converted into new particles. Okay? And they circle around this 16.5-mile tunnel 11,000 times per second. Okay? So going very, very, very fast. And we will do all that with magnets. Also, these beam pipes have to be evacuated so that they don't, you know, these protons, as they're traveling, they don't hit any air atoms, basically. Okay? So we want to really focus them and don't allow them to scatter around. Okay? So this is 10 to the minus 13 atmosphere. So, you know, a factor of 13 orders of magnitude less than what we have here right now. And you actually have to go a little bit beyond the moon to actually get that type of vacuum. Okay? So ultra vacuum. And also ultra cold. We use these magnets to steer around all these protons, okay, and accelerate them. And these magnets are in superconducting mode, which is basically meaning that they're super cool, just a couple of degrees above absolute zero. And that way we can inject a lot of current, electric current in them, and then they transfer it without any heat loss, okay, and very efficiently. And that's why we use this. Okay, so we have basically 16.5 miles of ultra cold and ultra vacuum. Okay, and that's why this is also very helpful for industry. So, you know, in principle, this has no other application than just pure knowledge. But a lot of industries want to come and help us build these things so that they get this type of industrial knowledge, basically, so that they can then apply to whatever industry they want to. So let me then just very briefly flash here a little bit of the numbers. So the energy that is stored by all these protons traveling at this very high speed in the LHC is similar to a aircraft carrier traveling at 5.6 knots. Okay, so that's not a lot, you would say, but the idea is that they're packed. That whole energy basically is packed into tiny, tiny, tiny particles. Okay, and that's the trick. These magnets weigh 43,000 tons, which is also like half that aircraft carrier. They basically cost the same to build, and the magnetic field that, you know, we have in these huge magnets, so that we can bend around and steer these protons, is 100,000 times or almost 1,000,000 times bigger than the Earth magnetic field. Okay, so here now we have a magnetic field that if you put a compass, it actually feels it, of 5 × 10⁻⁵ Teslas. These are the units for this magnetic field, and here we actually create 8 Teslas in these magnetic fields. Okay? That's why we have to be superconducting. And finally, some of the biggest misconception when we give tours of people at CERN is that, well, but this has something to do with creating energy. And that's not, that's absolutely not true. We're basically consuming all the energy that we can. We're not interested in new forms of energy to solve the oil problem or anything. We're actually just trying to consume a lot of energy to actually accelerate this, and then smash this into pieces to see what's in the interior, right? So we basically consume like a quarter of a normal nuclear reactor, basically. So this is basically like a quarter of the consumption of Geneva goes basically to CERN. Okay? So we are, consumers, not donors of energy. Right? Okay. So now we've been able to accelerate and collide these particles. How do we detect them? Oh, actually, before we go there, let me show you a video of that so you can see it. So, all right. So here you have the chain of particles and how they're going to be accelerated from basically being produced to then these very huge energies. So first they go to this booster ring, which is only 157 meters, and then it accelerates them just very, very tiny. Okay, just 1.4 giga-electron volts. Okay, the mass of one proton is 1 giga-electron volt. Then they go to a bigger one, which is the proton synchrotron, the PS, and that goes to 25 giga-electron volts. And then from that, they go to the super proton synchrotron, which is now 7 kilometers in length, and they get a whopping 450 giga-electron volts out of that. We can basically generate them in these smaller ones, then put them all the way up here, and then keep them accelerating here. So every turn they give, we kick them, and then we accelerate them a little bit more. And we can keep them then for hours. Okay? Actually, by the way, in this accelerator, in 1983, that's where it was discovered that the W and the Z existed. Okay, so these W and Z bosons were discovered here, okay, in this accelerator. But then later on, they built this huge tunnel, which is now the next step, which is the Large Hadron Collider, and that's the 27 kilometers. Okay, so here now we can keep these guys circling around for like 12 hours. Okay, so we inject them from this smaller energy to this bigger energy. We, in 1 hour or so, accelerate them to these 7 tera electron volts final energy, and we can keep them then colliding for 10 hours, basically. Okay, and then record all that data as that happens. So now this video is going to zoom in inside this tunnel, 100 meters underground. Here you see the graffiti of the standard model theory. Now you're going to cross the border between Switzerland and France. Okay. And then you go inside the beam, and that's a proton made up of 3 quarks, each of red, blue, and green. And now we're zooming out as we're going to hit one of these detectors, basically. Okay, so let me stop there. So we're going to see here the proton coming in from here, and then another proton coming in from the other side. And this is 100 meters underground. This is 6 stories high by 6 stories long. Okay, and that's going to happen a collision in there. Okay. So there you see the other proton coming from the left. Now we're zooming in, and boom, they're going to see each other. Those 2 protons hit, and then produce these hundreds of particles, new particles. Okay. Some of them are just muons, some of them are electrons, some of them are quarks. But we hope that once in a while we produce new particles. And as these particles travel out in this detector, they're going to leave signatures that tells us what they are. Okay? And so in this case, for example, as you'll see later, we've basically produced 2 electrons and 2 muons. Okay? So that's basically what's happening. Now, that's a very simplified picture. You only see 1 proton and 1 proton there. We actually have 10 to the 11 protons in something that is 20 micros wide and 1 centimeter long. And then 8 meters later comes another packet of those. Okay, so with 10 to 11 protons, and then 10 minutes later, another 10 to 11 protons. And then from the other side, the same. And so what happens is that one of those protons in the 10 to 11 will see the other, boom, and collide. Okay? But then the rest pass through each other, and then that's why we can keep doing that for hours at a time. Okay? All right. So let me then go back very quickly into here. So this is basically the picture of that detector. This was a picture taken in 2009 when all these repairs were going on. And so this is basically the real thing. This is another picture where perhaps you can see it better. This one is a little bit smaller than the other detector I showed you. This is the CMS. And so again, here you see this is like 4 stories high and 4 stories wide. And this is a huge solenoid magnet that we want to have a huge magnetic field also inside this detector so that we can bend charged particles. Okay, and we'll talk about that a little bit later on. So this is basically the largest and more powerful magnet ever made. Okay? We can create 4 Teslas in a volume of 12 meters times 6 meters. Okay? I mean, in the lab here, we can easily do 1 Tesla on something like a centimeter square. But imagine doing 4 Teslas on 6 meters times 12 meters. Okay? It is absolutely humongous. Okay? This thing alone weighs 12,000 tons. Just to give you an idea of the engineering involved in here, this is a cavern 100 meters underground. Okay? When they dug it up, they had to think that when they, because it was, the detector wasn't built there, of course, when it was dug, and so the floor sunk like 15 centimeters when they built this thing and when they lowered all these detectors inside. Okay, so they had to think that this floor is going to give way like 15 centimeters, so that the new beam of particles would come in and basically be everything aligned within microns. Okay, so just the engineering of this whole thing is just mind-blowing. Okay, that's why you need huge labs. No one country alone can do this. This is why you really need this huge collaboration between many universities and other countries. Okay. Also, the whole detector, when they turn on the magnet, it has 64 atmosphere basically coming down. Okay, so you also have to be very structurally sound so that things don't move around too much. Yeah. And the energy is basically like that aircraft carrier moving now at 20 miles per hour. The energy that it spends. Okay. All right. So how we detect this particle? So here you see a cutout view. What you have here is that the protons will collide in here, and then the particles will be produced. And then depending on what they do in these detectors, then we're going to know what they do. The first thing we do is just have a silicon tracker that basically tells us where these charged particles went. Then we stop electrons and photons, and then we stop the hadrons, basically, so anything that has a quark. Okay? And then here's this superconducting magnet that creates this huge magnetic field in this volume. Okay? And that's why these particles are bent like that, because they have to travel through this magnetic field. And if you have a charged particle, if this is, for example, plus particle, it does this, and if it's a negative particle, it bends the other way. Okay, so we can tell apart whether this particle is positive or negative thanks to this magnetic field. Now, on the outside, the only thing that can get out of this superconducting magnet, basically, are muons. Okay, so all electrons are stopped here, and photons. All quarks and protons and everything is stopped in here. So the only thing that can pass through is muons. Why? Muons are from the second generation, and they don't interact with things from the first generation. So they, boom, they just pass through. Right now, through you, you have around, like thousands of muons passing through you every second. And, nothing happens, basically, because they just don't interact with us. Okay, so they just go through, okay? And you see that they're bent in one direction inside, and then bent in the other direction on the outside. Because here, the magnetic field is basically reversed. Okay? And so let me then show you a little demo of this as well. So if you shoot an electron, for example, that's what it's going to do. It's going to be bending in the silicon, and then it's going to be stopped in this electromagnetic accelerator. If you then shoot a charged hadron, for example, like a pion or a proton, it will get past this electromagnetic calorimeter and then leave some energy in the hadron calorimeter, so it will be completely stopped. And then if you have a muon, it will go through, it will bend in one direction inside the solenoid, and then it will bend in the other direction in this other solenoid, in the outer solenoid, and then basically just leave you tracks in these chambers. As this charged particle passes through, it basically leaves a spark, and that we can measure as well. Okay. Okay, so we've done some contributions to those detectors here at University of Rochester, basically working on the silicon and this Hadron calorimeter that you've seen there. And I think I'm going to just stop there and then go on a little bit more into what we're going to be doing later on for the MasterClass. Okay? So now if you want, what I'm going to show you here are actually that these particles are very real. And so if you can come in now here, or at least do it with groups. Okay, so okay, so I mean, basically let me see if, so the basic idea here is that we have evaporated alcohol, and so it is very, very cold downstairs, and so it's basically being evaporated, and so this creates little bubbles of this alcohol. So the source is not very strong. I'm not seeing a lot of. Okay, anyway, so let me then explain you the principle, and you can see it here. I think it's too hot, yeah, Yeah, so the idea is that, you have liquid here, it's evaporating, and then these bubbles are in a metastable state. What that means is that if any charged particle passes through it, it will basically condense that bubble and make a little droplet that then we can see, okay? And that's basically the principle that, many of these detectors are based on. That, when a charged particle passes through, it ionizes this material, this gas.
If you look at the rod down here, you can see the rod right down here. See this rod down here?
Yeah, but I've seen those videos, and it's amazing. It's beautiful. And in most science museums, they also have it. So it's really very cool. Okay, so are there any questions before we move on? Did you have any questions about activities today, or the standard model, or CMS, or anything? No? Oh. Because they're so small, basically. Okay, so it's like the bigger bag, if you want, proton is not really that doesn't really matter. It's basically all these little quarks with all these little quarks that then boom smash together. Okay, so these collisions are really of these 3 quarks and then the other. And actually, at these energies, it's not even the quarks. Sometimes you also see the gluons in between these quarks. Okay, and so what you're colliding is one of these gluons with the other one of these gluons. We'll talk a little bit more about this later on. Okay. Any other questions? Yes.
Is there any repulsion because they're both proton-proton?
That's a very good question. Yes. That's right. Yes. So there is, you have to, take this into account that, because they're 2 positive electric charges, right? They will tend to be repelled. The idea is that yes, but you're basically you're constraining them, you're focusing them with these optical lenses basically in these magnets. Okay. So you're packing them together in a very small volume, right? And then 10 to the 11 of them, right? So yes, I mean the cloud, that little bunch, what we call this bunch, it's a cloud of protons, and they're kind of smashing around together. But that's why we circulate them for hours, so they will clean up the outliers, basically the ones that have a little bit more transverse energy, and then they get kicked out basically, with these interactions. But ideally, basically, what's happening, they're focusing them with these electromagnetic fields, basically, so that they're bent and accelerated at the same time, and then all keep in this very small volume. So yes, there is repulsion, but we can manage it.
I was going to ask, was there any advantage to Fermilab having anti-proton and proton collisions, or is it the higher energy outweighs that advantage?
That's a good question. The problem with antiprotons is that it's very difficult to produce them and keep them for hours. Okay, so because it's an antimatter, you have to isolate them from any matter, or it will disappear. Okay, so we can't produce them easily. The problem is how do you store them for hours, right? So that was the drawback. It's not a problem of energy. I mean, you could have built a big accelerator here with antiprotons as well, and that's okay. The nice thing of the antiproton is that you only need one beam, because they're antiparticles, so you can have the protons going in one direction and the antiprotons going in the other. Okay, basically in the orbits, which are separated by like a few millimeters. Okay, here because you have protons, you have to have 2 separate beam packs, and that's what I showed you here, right? And so in one beam pack, you have protons going in one direction and the other in the other, and then you then focus them together when you want to collide them. Okay? But yeah, in principle, you could have also built an LHC with antiprotons. The problem is that you can produce, 2 sets of protons if you want in like no time, and then to generate antiprotons, it would have required many hours, a lot of care, and then it's not efficient. Okay. That's yes.
Why would when you collide the two protons together, why would they go towards a bigger particle that had 10 times slower?
Because the energy is so big. Okay, so we're smashing 2 very small quarks, but basically with very high energy. Okay, so we're starting off from this energy, right? And then we can produce masses that are here, which is way above my initial mass for the quarks. Okay, so that's the whole point. We're giving them energy by accelerating them, so that we can transform that energy into heavier particles. Right? That's right. Any other questions? No? Very good. So then now we're going to start some of the lab tours and other particles like electrons and muons and things that we already know about. So this is a little, you should see this as a little movie. So imagine that you have this blue heavy particle that is traveling upwards, for example, And then in this point, it then decays into two smaller particles. And so then they go away like that, okay? And all these tracks is basically what we're going to be seeing in these events, okay? Now, can you tell me what conservation laws apply when this, big object that is moving in this direction then decays into two smaller objects? Anyone? Momentum, very good. Any other? Charge, very good. So this is supposed a neutral particle, and then it decays to a positive one and a negative one as well, okay? And any others you can think of? Mass. In this case, that's not quite true, okay? So mass is actually doesn't have to be conserved, okay? So you can convert some of the energy, right, some of the velocity, if you want, of this initial particle into also, more mass, basically, for the incoming ones, okay? So energy is conserved, that's right. So energy is conserved, and momentum will also be conserved, okay? But not just the mass, okay? So it is not true that this particle weighs 100 units, for example, and then these two will weigh 50, okay? That doesn't have to hold, okay? Okay, so very good. So we have charge, energy, and momentum, okay? So there are also some other type of events that you also have to see that are not the ones that you're looking for, okay? So these tend to be the most common types of events that we see when you collide these two protons, and it's just basically that you produce another quark or gluon, and then these become showers of other particles, okay? And we call them jets. And so this is basically, again, a quark that is produced, and then immediately it grabs other particles, basically, from the vacuum, which is, very interesting in and of itself, and then produces, like a shower of other particles. And we detect those as jets. And here you have an example. So again, this is a view of, like if you were one of the protons coming in, and the collision happens here in the center, and then you see here all these yellow tracks that are coming out of this collision. And then here we've drawn, to guide your eye, some cones that these are these jets, basically, okay? So here, for this cone, for example, with this direction, basically emitted one quark that then immediately produced many, so 50 or so other particles, and then they travel this distance, and then they are absorbed in this calorimeter, okay? And here you have several of them. So here you have even like 10 jets or so. And these jets can also have inside them some muons, okay? So remember the muons we saw, they are the ones that can travel past the solenoid on the calorimeter and then hit these muon chambers out there. Okay, so you have here one muon inside this jet. Okay, so you will have to be careful that you may find some of these events there also, and this is not what you're looking for. So then let's concentrate more on these W and Z particles. So we said that they are the mediators, or the ones responsible for carrying the weak interaction, and there's three of them. So you can have a W that is positively charged or negatively charged, and then the Z, which is just neutral, okay? And then we also said that the range of interaction is very, very short. So they are going to be produced, these Ws and these Zs, with these very high energy collisions, and then immediately decay. Okay, I guess I'm going too fast here. But anyway, so let me then just say something more about the W boson. So the W are responsible for radioactivity. So for example, when one nucleus basically transforms a proton into a neutron or a neutron into a proton, it is because we have an exchange of this W boson. Okay? And actually, without them, the sun wouldn't shine. Okay? It is thanks to these particles that we can convert 4 atoms of hydrogen into 1 of helium. This is fusion process. And that gives us tons of energy in forms of the photons that are emitted. And that only can happen thanks to this W boson. So the way it happens is that you turn one of the protons, so the nucleus of the hydrogen is a proton, you turn one of them into a neutron to form deuterium, and then you collide it with another proton to form helium-3, and then you combine 2 of these helium-3 to produce several of these helium atoms. And that's basically what's occurring in the sun. So it's thanks to these particles and this force that actually the sun can shine. Yes?
In what way does the boson turn the proton into a neutron? Like, does it get the quark from a different source, or?
Well, so it is these collisions, right? So you have these 2 protons coming in together, and then they'll basically exchange a boson, or one of the protons will then basically give off a W boson and then become a neutron. Okay, so it is really a collision. Okay.
Right. So in like I just don't, in what way is the basically quark turned from an up to a down, like in that process?
So that is mediated thanks to the W. Right. So there you conserve the charge and everything, and that's how you do it. Yeah. I mean, it's like one of your chemistry reactions, right? Where you add whatever sodium and chlorine, and then boom, that's yeah. Okay. All right. So then the Z bosons are then also responsible for some of these nuclear reactions, but then they basically just don't exchange any charge. So for example, when you produce one of these Z, it will just, because it's neutral, it will decay, for example, to an electron and a positron, or a muon plus and a muon minus. Okay. So this is basically, and you have a cheat sheet with you, this is basically what you're going to be looking for. So we're going to be looking for a production of a Z that then decays to an E plus and an E minus, or a mu plus or a mu minus, or a W that then decays to a muon or an electron and then a neutrino. Okay? In CMS, we can actually detect electrons, so basically they will be short tracks and then they leave all the energy in the first layer, the electromagnetic calorimeter, or muons. Muons are the ones that travel all the way and then don't interact, basically. Okay? It's only because they're charged and then they leave these sparks. Okay? And then finally, we have these neutrinos, which are also emitted in the Ws. And these neutrinos don't interact with anything. Okay? So right now you have, I think it's 10 to the 13 or something per second per centimeter squared coming through you because of the sun. Okay? The sun, as you just saw, is constantly emitting these Ws, and then it's a huge source of neutrinos. Okay? And so these interact with nothing. I think you have 50 light years of lead, and you would get one neutrino to interact once with all that matter, okay? With the energy that the sun produces them. So they basically can whip through anything without interacting, okay? And so, of course, they don't interact at all with CMS. And so how we detect them is by measuring all the rest of the energy that we can see, that we're recording in our detector, and then summing it, and then see if there's anything missing. So that's what we call missing energy. And that's the signature for these neutrinos. So let me show you then some examples. So this is, for example, a W to electron neutrino. Here you have the end view, and here's a side view where protons are coming from this, from here, and then they collide in here. So you see that there was an electron emitted. So this is the track that went up, and then a lot of energy was deposited in the calorimeter. And then here you have a yellow arrow, which is basically giving you off the missing energy. So basically this yellow arrow signifies where the neutrino went. Okay? So in this case, you see that you can tag this event as a W going to an electron and a neutrino. Now you will see that there's also these extra tracks. This happens because you can also produce all these other quarks together with these Ws, for example. Okay? But in your displays, you will actually be able to turn them off so that you can really only concentrate on this electron and the neutrino, for example. Okay? But in principle, you also have all these nasty tracks going around that you have to kind of filter somehow. And then this is a Z to mu mu case, where here you have, so again, remember the muons, they're not stopped by the calorimeters, they just keep going through past the solenoid and everything, and then they leave these tracks in these muon chambers, okay, these sparks. And here is again that view where you produce the Z here. The Z, again, it lives very, very, very small time, okay? It decays absolutely immediately just after it's produced, and then it produces two muons, and then these two jets that I was talking to you about. Okay, and here you see these many, many other particles. Okay, so this is, for example, another case of a real event. Okay. All right. So this is now the tool that you're going to be using that you have in one of the tabs of your computers. And so you basically need to familiarize yourself a little bit with the display that you're going to be seeing. And here you have several other commands to turn off the different parts of the detector and tracks that you can see. Okay. So actually, today we're going to be seeing if we can distinguish a W from a Z event. So for example, here you have a neutrino and a muon. So this is a W to mu nu event. And here you have one muon and another muon. So this must be a Z to mu mu event. Okay? So that's your job. Tell apart these two, right? And remember, and you have also several examples there, these are the keys. So Z's won't have neutrinos, and W's will have neutrinos on only one lepton, okay, or a muon or a positron, or an electron. Okay. So that's one of the first cases. The other one, you will have to say, of course, whether you're saying an electron or a muon. Okay. So in this case, this is the electron. So it's just a very short track, and then it leaves the energy in the electromagnetic calorimeter. That's the blue ring in this XY view. And here you have, again, and then this yellow arrow is the neutrino. Okay, so in this case, this would be a W2 electron neutrino. And now in this case, you have, again, the missing ET, the neutrino, this yellow arrow, and then this muon. So again, this is the calorimeter, this brownish ring. That's supposed to be the hadronic calorimeter. And then if you see anything past it, that means that there was a muon in it. And with this layer there for the tracks. Okay. Another thing that you will need to do is to tell whether the electron or the muon is positive or negative. Okay? So here I have an example, and here you have to be careful. You have to put them in this x, y, z view, where the x and the y are in this plane and z is coming out. And in that case, and in that case only, if this red track bends clockwise, that means that the particle is positive. Okay? This has to do again with the direction of the magnetic field. Okay? And if you see a negative track that will bend counterclockwise, so upstairs like that, then that means that that one is negative. Okay? You have to be also careful because then the bending direction after it's left the solenoid, so here in the muon chambers, goes the other way. Okay? Whereas for electrons, it's just one way. Okay? Because they get stopped in here basically. Okay? So sometimes you may have to zoom and then use a straight ruler or the edge of your page, of your sheet, to actually tell whether this thing is bending in what direction. Okay? And remember, the rule of thumb is in this view, x, y pointing up, x to the right, if it bends clockwise, then it's positive. Okay? And you have this in the cheat sheet as well. So that's a task. And then finally, for whenever you say that you have a Z, then we will be able to measure the mass of that Z boson. And in the end, what we want is to plot this, that quantity, the mass. Okay? And then we'll make this plot and then share it with other students that are now at Fermilab. Okay? So why don't we then get started, and then, so you should split into groups of
Noon! We got this, dude. Alright. So, Jameson, what should I click? Just start clicking stuff on.
All right, so are you guys there?
Kinda. How do we clean it up again?
Unclick that off. Unclick that off. What are you doing?
Yeah, so you guys have cleaned up the tracks, you have to go all the way down, and then click on listening to the That's the last one. There you'll see very empty. Are you sure you haven't cleaned anything else?
Yes.
No, you gotta clean everything.
Leave it like that when they got one.
Actually, why don't you start again?
Anyways, spaz out.
All right, so
Something that was clicked. You had to click the top one off too. Oh great, now we don't know which one.
okay, so please
Should be freaking on.
We got three?
Oh, we got more. We got way more than 3.
We got three. We got 13.
So Chris, what did you think of this event analysis?